The binomial distribution is a specific distribution where basically you're breaking things down into two solutions almost, or two types of solutions you get. Basically, when you flip a coin, so if we were to flip a coin, what choices are we going to get for a solution? We're either going to get heads or tails. We're talking right now about binomial too. If a woman has a child, they're either going to be a boy or a girl. But what happens when there are not some things that are just two different choices? Well, you can look at it, or it can be derived down into two choices. For example, surgery can be considered a success or a failure. Your blood pressure, you can have normal or abnormal. So even with things that aren't quite so black and white as having two types of solution, or two types of outcomes is what I should be saying, we can break it down by thinking it like this. So a binomial experiment, there has to be a fixed number of trials. You have to, test 20 people or, 100 people. Each trial can only have the two outcomes. To be binomial, it has to have two outcomes. Or it can be reduced to two outcomes, like we were talking about here. And they can be considered success or failure. The outcomes must be independent of one another. Flipping heads or tails in a coin, they're independent. The first getting heads does not affect the fact that you're going to get heads or tails the next time. And you can't change the probabilities. The probabilities of success must remain the same. So before, when we've done stuff with probability, or drawing a card out of a deck of cards and not replacing it, well, that's changing the probability. That's not going to work for a binomial experiment. The outcomes of a binomial experiment are called a binomial distribution. And we have all this great notation. Some of it we're familiar with, maybe some of it we're not. Basically, we're going to take the probabilities of successes and the probabilities of failures. P, this is the big one here, is the numerical probability. Q is numerical probability. I'm sorry, P is success, Q is failure. Keep this in the back of your mind for a little bit later on. The probability of success equals P. The probability of failure is going to be 1 minus P. Again, probability is still out of 1. It's still out of that 100%. So if we know what the success is, we can figure out the failure by going 1 minus that. And actually vice versa. N, no N, it's the number of trials. X is the number of successes. So using all that notation leads us to our binomial probability formula. It says in a binomial experiment, the probability of exactly X successes in N trials, so probability of X, the successes, is you're going to take the factorial of your number of trials over the number of trials minus your successes factorial times the number of successes factorial times your probability raised to those successes, and your failure raised to the number of trials minus those successes. Kind of see why we're going to use all this terminology, because trying to explain it is a little bit difficult. But we do want to focus right here on this formula. In fact, I'm going to grab that formula real quick so I can use it. All right, so let's look at an example. Coin is tossed 3 times. Find the probability of getting exactly 2 heads. Now, this is a problem we've done in the past. If you look at the sample space, these are all the possible outcomes. 3 heads, 2 heads and a tail, head, tail, head, tail, head, head, tail, tail, head. You get the idea. And there are 3 ways to get 2 heads. So this is a problem we've done in the past, and we would find our probability of getting exactly 2 heads is 3 out of 8, or 0.375. If, in this case, well, let's look and see why this worked, why this is a binomial experiment. There are a fixed number of trials, 3. There are only 2 outcomes for each trial, heads or tails. And this is all going back to what makes a binomial experiment. And I'm showing you right now that this one works. The outcomes are independent of each other. No way, whatever you toss the first time doesn't affect the second toss. And the probability of success is 1/2. You have 2 outcomes, one of them is heads. So let's look right here. We have 3 trials, that's our N, the number of successes. We want 2. Our probability of success is 1/2. Our probability of failure is 1/2. If you were to put these all into this lovely formula here, we would get the exact same answer. Which in this case, why go through all this work? Well, this one is just showing you that it does work based on something we've known in the past. Let's try an example. A survey found that 1 out of 5 Americans say he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. Well, let's remember our formula. And actually before that, what we need to do is let's pull out some information. Basically, look at what we need to know. We need to know what N is, the number of trials. We need to know what we want, what our success is, and then we need to know our probability and our failure. It's not as complicated as it looks once you kind of get used to it. They're selecting 10 people, so the number of trials we have is 10. Our successes, what do we want? Well, we want exactly 3 people who visited a doctor. Our probability for that success, that's right here, 1 out of 5. Now, if our probability for success is 1 out of 5, that means 4 out of 5 are what we'd consider failures. Once you have that, we just need to plug it into this formula here. So, we want the probability that we're going to have 3 people. We're going to take our trials factorial over, and then just start filling things in. 10 minus 3 factorial times 3 factorial. All of it multiplied by our probability, 1/5, raised to our number of successes, 3, times our failures, 4/5, raised to, well, the number of trials minus the number of failures. In this case would be 7, 10 minus 3. Whew. And then once you take your time and figure all of that out, we're going to find that our probability of getting exactly 3 people in this binomial distribution, about 0.201, almost 20%. And that's going to tell us what, well, basically it tells us what our probability is of selecting exactly 3 people. Let's look at one more example. Survey from the Teenage Research Unlimited found that 30% of teenagers consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. At least 3. We've seen that term at least before. And remember, when we did this last problem, it told us exactly 3. Focus on the fact that this says at least. What does it mean when we say at least? All right, well, let's start figuring out the things we know. We need to know N. We need to know the number of trials. 5. We picked 5 teenagers at random. We need to know the number of successes. Since it says at least 3, we want to know when there's at least 3 receive their spending money from part-time jobs, or 4, or 5. And the reason for that we're going to find all 3 here is because it says at least 3. Could be 4, could be 5. Our probability is the 30%, so I'm going to write that as 0.3 or 0.30, and our failure is going to be 70%, since 30% is probability, or 0.7. Now, just go through the formulas, and I promise I'll show you maybe a little shortcut way later, but we do need to practice this. So once you find these probabilities, and once you identify this, it's really just putting things into your formula. So we're going to take 5 factorial, here's our formula here, I'll put that up top, 5 factorial over, let's start filling things in, 5 minus 3 times 3 factorial times 0.30 to the third times 0.70 to the second. Again, that's our difference between the trials and successes. And what that does is it gives us about 0.132. All right, now do the same thing for the probability of 4. And again, all I'm doing here is using my formula and plugging in the variables I've identified. Oops. Oops, and I already have my little mistake here. Watch what I copy. Remember, it's the number of successes, and this time that's 4. That works out to be 0.028, and one more. And then once we get done with this, we can talk about what we do with all 3 of these probabilities. Okay, remember, to be a binomial experiment, they have to be independent. So if they're independent, we're thinking about adding the probabilities. So to find the probability of at least 3 earning their money from part-time jobs, you basically are just going to add all 3 probabilities together. And when you do that, we get an overall probability of... So, focus on your words. Use your formula. Focus on the words. If it says exactly, do the formula once, you're good. In both of these, remember, though, how I've identified the variables first. If it says at least, no, if at least, it could be 3, 4, 5 in this case. Do each of the probabilities independently, and then add them together.